Welcome to the weekend, everybody. A couple of announcements, decisions I've made. First of all, the exam is Wednesday, so be ready for that. The first thing, though, the most important thing is on the homework problems in Chapter 9. I just assigned this last lesson, and I technically said when it's due, but I'm assigning all three of these, but I am not going to collect them. We haven't got time for you to get them in and for me to get them graded and back to you by the time of the exam. So I am assigning them, which means you damn well better look at them. I will post the solutions on the bulletin board on Monday. And I will also post the solutions for the homeworks that just came in on Monday after the next group turns them in. Doesn't make sense to post the solutions before people turn them in, okay? So all of the homeworks associated with this next exam will be posted on the bulletin board, and certainly looking at them and understanding them is a good way to start being prepared for the exam. Of course, you have to do other things too. You have to understand some of the principles involved as well. It is typically the multiple choice that knock people down. That's what I often see. That's what happened last exam. And also the all or none. People making what I call stupid mistakes. If you made stupid mistakes, which means you looked at that and you go, how in the world could I have done that? That's the kind of thing that you need to avoid, okay? So the exam will be the same. Now, I haven't said it yet, of course, but you know there's going to be a problem similar to these. There'll be a problem involving Newton's laws and so forth, but you will have the opportunity to opt out of one of the problems. So there'll be 4 problems, and you choose the 3 that you want to do, okay? And the equation sheet will be attached to the exam. And that saves you the trouble of memorizing the equations, but you still have to know what to do with them. And that of course, the problem-solving technique, that is the key thing. So, once again, Monday, after the Monday lesson, I'll have all of the homework problems posted there. That gives you a couple days to take a look at them before the exam. The lab for the torque, I think if you've looked, I know some people have looked at it, it's very easy. But it's not due next week, it's due the following week. It's due the following week. So you can concentrate on studying this material for the exam coming up on Wednesday, okay? We'll do the same thing on Wednesday that we did before. Those of you in this group or on the video here, the video group, who chose to go over across the hallway, if you could do that again, that'll work great. It worked beautifully for us, so we're very, very happy about that. All right, what I really want to do today is finish Chapter 9, and then we're going to be jumping back to Chapter 5, 6, and 7. Okay, and you'll see that when we go to Chapter 5, it's really very different from what we've been doing. This Chapter 9 stuff is really similar to Chapter 4. So I want to do the 2 problems in here, which is the sign problem, as I call it, and the ladder problem. So let us take a look at these. Again, we do these problems so that you can learn some of the techniques that are used. And the sign problem is example 9-6. And in this problem, if you go down to downtown Frostburg, or actually any small town or certain sub-neighborhoods of New York City and so forth, you will see this arrangement. This is a way of hanging a sign. I call this the sign problem. It's such a common thing, it's a good one to look at. What we have here is a wall. We've got a wall. And there's a hinge on the wall. There's a hinge here. And then we have a beam coming out. There's a wooden beam. And in this case, the beam has a mass. It's 2.2 meters long. So the distance here is 2.2 meters. And the mass of the beam and I will call it little m, is 25 kilograms. I don't recommend doing what the text did, which is using a little m and a big M. I like to use an M1 and an M2. Unless you have a writing technique where you make sure that you can tell your little m from your big M. Otherwise you can get confused, and if you use one instead of the other, whoa, that's going to cause problems. Now, this is tied up with a wire or a rope, whatever, to the very end, which runs up here, and we're told that it makes an angle of 30 degrees. All right, and it's fastened up here. And then tied to the end is a sign. And what the hell, I'll call it Uno's, because I went to Uno's yesterday. I went to Uno's and I had one of their pizzas, thin pizzas, and man, I was in such a bum mood because of all this stuff going on. It just made me feel great. Okay, and the Uno's sign, what do they got here? Oh, they got Arlene's Bookstore. Okay, well, Big M is 28 kilograms. Big M is 28 kilograms. And the beam is 25 kilograms. The beam is 2.2 meters long, and the rope or wire is up 30 degrees from straight across. And what you want to find here are find all of the forces. This is the question. What's the tension in the wire? And you could say, what are the magnitude and direction of the hinge force? In this case, because it's not just friction here and so forth, there could be an X and a Y component to that hinge force. So you're asked to find the X and Y components of the hinge force and the tension, or equivalently, if you know the X and Y components of the hinge force, you can find the direction of the force exerted by the hinge and its magnitude. That's a vector problem from way back in chapter 3. All right? So we've got a reasonable picture here. Now we have to draw, so we got our picture, and now we got to draw our free body diagram. Once again, the question is, well, because it's a statics problem and nothing is moving, anything can be considered the object that we're going to draw the free body diagram for. But what we choose are the objects or the places where the forces come together. Well, the place where the forces come together is the beam. Everything is touching or influencing the beam. So we're going to consider the beam. We draw the beam. There's our beam. And now we have to draw sloping upwards, of course. That's straight. Closer to straight. Yeah. Gravity is acting on the beam. But we assume it's a uniform beam. We have to do that. So where is the force of gravity effectively concentrated? The center. The center of gravity of the beam is here in the middle. So what we have here downwards, acting on the middle, is little m times g. A little m, g. And we need to mark these distances. You need to mark all of the distances. Over here on the end, we know that this is pulling down, and we formally solved for it with the chandelier. I'm going to skip that step now. We know that the tension right here is going to be big M times G. Technically, we draw the free body diagram of the Uno sign. We get that the tension is equal to the weight of the sign. But I'm just going to skip over that part. So we know that out here is another vector downwards of big M times G. Then there is a tension this way. Now, let's talk about this. The textbook does this a different way. I'm going to do it my way. Somewhere in between my way and the textbook way, you'll see. The tension, we know the direction of the tension. It has to be 30 degrees up. Ropes pull, right? Ropes pull. All we need is the magnitude. One unknown. So I'm going to draw it like this. Like that. And I'm just going to call it, I'll call it FT, or they call it FT, so I will too. Generally, I just call it capital T, but whatever. And we need to draw this angle. It's 30 degrees. Then there's the hinge force. There's the hinge force. The trouble with the hinge force is we don't know the direction of the hinge force. And we don't know the magnitude of the hinge force either. Now, we could either put in, we could draw it like this, and we could put in an unknown angle and have to solve for the angle. But it is equivalent, remember that knowing the two components of a vector is equivalent to knowing the vector. If you know the two components, you can find the angle and the magnitude. Okay? So, we know that the hinge is not going to be pulling, it's going to be pushing. So there is an x component to the hinge force, right there. Do they use capital H? They use FHY. Oh, heck, man, just call it HX and HY. And then there could be a vertical component. Now, this is interesting. Depending on the arrangement of the stuff, the hinge force could be up or it could be down. The vertical component could be up or could be down, depending on where this sign is attached and so forth. But I think what you can see is, if this were frictionless, because gravity is pulling this way, that it would fall. So most likely, the y component is upwards. Now, if you're not sure, you assume a direction, and if you get a negative sign, it means that the actual direction of the force is opposite what you assumed. So at the moment, we'll just assume it's upwards. But if it turns out it was downwards, we'll get a negative sign for this, and that's perfectly fine. Normally, when we label these things, these are the magnitudes of the forces, not the components. Okay, not the actual component values. They're the absolute value of these things. So if you get a negative sign for an absolute value, it means your assumption of the direction was wrong. You don't have to redo the problem. You just say, my assumption was wrong. I had it drawn up. Therefore, it is down. Okay. Yes?
I might have missed it, but how do you know that the hinge is pushing instead of pulling?
Okay. Look at the x components. Does this have an x component? Does this? Does this? Does this? Which way is it? To the left. So what's the only thing left to counteract it? The hinge. So this is the thinking that's left out in the textbook. You say, how do they know that if this is a pin here, this thing could be pulling. It could be pulling on it. It could be pulling on it. But since the x forces have to cancel out, we say, well, this is going this way, so this will counteract that. So any other questions? These are the little things that you can look at and go, how the hell did they know that? Well, there was some analysis done. Yes?
How does a hinge actually pull something? Doesn't it just allow something to move on a fixed?
No, it's attached to the wall. It's physically fastened to the wall. If it was just pressed against the wall, it could not pull. But see, I drew that there just to show that it's fastened to the wall. So it can exert a force in any direction. That sucker isn't just pressed against the wall, it is fastened to the wall, glued to the wall. So it could push or pull. Okay? Picture, free body diagram, coordinate system, might as well use the usual. Okay? Immediately, we can consider the sum of all the x components. Now we apply the conditions of equilibrium. As I say, the best thing to do is to apply the first condition of equilibrium initially. Don't use torques unless you have to. If I apply the first condition, this says that the sum of all the x components and the sum of all the y components must be 0. So if I say the sum of all the x components is equal to 0, well, now we see that we have a plus at hx, and then if we break this into its components, the x component of this tension force, this is the adjacent, this is the opposite, and this is, of course, the hypotenuse. Adjacent means which trig function? Quick, adjacent goes with cosine. You should be able to do that automatically even if I burst you out of your bed at 3 in the morning. So it's, and is it positive or negative? It's negative. Minus ft cosine 30 degrees. So there, it says the x component of the hinge force, bringing this over, is the tension force, but we don't know yet the tension force. But once we get, if we get the tension force, somehow, then we will put it in here and we'll get the x component of the hinge force. All right, but we're not finished yet. Now, if we do the sum of all the y components, that equals 0. And we got a lot here. We got an hy plus hy. Then we have a minus mg. And we also have a minus big mg. And then we have this component pulling up. We've got this component pulling up here. And so we have a, and it's the opposite, so we have a plus tension force sine of 30 degrees. Okay? Let's just leave it like that. Okay? Let's just, and I'll make that more like a plus sign. So there's another equation. So what does this tell us? It tells us once we know the y component of the hinge force, we know this, we know this, we know the sine of 30, we can find the force of the tension once we know the y component of the hinge force. But we don't know that yet. So we got 3 unknowns. We're actually going to have 3 equations, oh my gosh, and 3 unknowns. Don't worry yet, okay? 3 equations and 3 unknowns. But once we get the tension force, we could find the y component of that. We could also find the x component, okay, from that. All right. We ran out of the first condition. So when you run out of number 1, where do you go? Number 2. You go to number 2. Okay? So now we've got to use the second condition of equilibrium, which says that the sum of the torques about any pivot that you choose is going to be 0. Now, any pivot can be chosen, but there are a couple of places here where it really is a no-brainer to put the pivot. When you choose a pivot, any force applied to that pivot produces a torque of how much? There's a good multiple choice question. Once you choose a pivot, it produces a torque of 0. Well, I see two places where multiple forces are applied. What are they? The left side's got Hx and Hy, and the right side, right end, has got Ft and big Mg. That says if I put my pivot here, the tension force will not be in the resulting equation. And as a matter of fact, if I put my pivot here, will Hx be in the equation? Where does the line of action of Hx go? Right through the pivot. Okay? So what the hell? I'm free-forming now, which means I could screw up, so you got to watch me. Okay? I'm going to put my pivot at the right end. Okay? So over here, the sum of the torques, and you must tell me, you must specify, the sum of the torques about the right end is 0. All right. Ft does not produce a torque. Big Mg does not produce a torque about that point. Hx does not produce a torque about that point. This is almost the ideal point. These only Hy and little mg are in this, right? Well, hell, that's going to be easy. So, looking at Hy, does it produce, now here's our pivot, is this a, I'll put our torque there, is this a positive or a negative torque? If this were the only force acting about this point, what would it do? It would go clockwise. Clockwise is negative. Negative. The angle here is 90 degrees. The distance is 2.2 meters. So it's Hy minus Hy times 2.2 meters. And this one is going to produce what sign? Positive. Well, how can you tell it's got to be positive? Because you got a negative, you better have a positive if it's going to add to 0. So we have plus little mg times 1.1 meters. And this again is 90 degrees. So that's it. Okay? And if you solve that, I believe somewhere they did this here. Yes, all right. When you solve that, you get 123. Let's just do it. What you get is Hy times 2.2 meters equals mg times 1.1 meters. And the meters cancel. And this says that Hy is 1.1 over 2.2 times little mg, which is 1/2 of little mg, which is 1/2 times little m is 25 kilograms, 9.8 meters per second squared. And I believe that is 123 newtons. Hot dog. Yes.
You push the computer screen down.
Did I what?
You push the computer screen down so we can see the bottom of the desk.
Oh, I hate this thing. Yes, no? Can you see it? Perfect time. Are we checking? Yes. All right, we've got HY. Well, quote, I'm going to leave it to you. You take this and you put it into there, and you put in little mg, big MG, and you solve this for FT. Do people see that? If you know HY and little m and big M, you can move all of this over and divide by the sine of 30, and you can solve for FT. And then you take that, once you have that, and you put it in there, and you find HX. And you're done. Then you're done. Okay? By being clever, by noting that the line of action of this force goes through that point, and these are applied at that point, this don't occur in the final equation, and you can find that. And it turned out to be positive. And you can see what's happening is, this thing wants to go down. It wants to go down, so this is holding it up. This is holding it up. And is it, Brianna? That it's pushing because it's offsetting the tension. So at this point, see, once you get to the equations, the physics is done. The physics is doing this. The physics is this. The physics is that. That gives you the equations. Then it's a math problem. In this case, you've actually got 3 equations and 3 unknowns because you're clever. One of the equations you get right away only involves one unknown, and you can solve it. Boom. And then you can put it in the next one and get the next. You can put that in the next and get it, and you're done. That doesn't always happen, but it does in this case. Let's go and let's look at the ladder problem. Ladders, people, are dangerous. My house is 3 stories high in the back. It towers. And it is a nightmare to paint that house. If I ever do it again, I'm going to buy one of those things you drive around and that you can, with a bucket on it or whatever. I'm not doing it from a ladder anymore. That's crazy. Okay, that's nuts. Okay, but someday I love my house, but someday I'd love to have a ranch house and never have to go up or downstairs again. But that ain't going to happen. You know how hard it is to move. Wait until you've been in a place for 30 years and all the garbage that you've collected. All of that stuff. Anybody ever watch American Pickers? I've been in a house like that. Not mine, but I can't believe some of the shit that people live in, okay? So I can't give that up. I only got 2 of that. If I sell you that, I'll only have 2 of them, and I got 3 right now. Okay. The ladder problem. This is example 9-7. Another classic case that does occur out there. And in this case, what we have is a ladder up against a wall. And it's 5 meters long. That's, yeah, mine's about, I've got one that's about like that, okay? I got one that's 32 feet. That's more like 10 meters. It's really long. It's sitting like this. And we are told that it is 4 meters from the ground to the top of the ladder. And actually, it's not quite that steep. We're told that the bottom is 3, are we told, let's see. All right, it leans against the wall. Oh, the ladder is 5 meters long, right? Yes. So we have a 5-meter ladder. Touches up here 4 meters above the ground. And of course, there is friction down here. There better be friction. What will happen if there isn't friction down here? Okay? And this is interesting. We have to make this assumption. No friction at the top. It turns out if there's any friction up there, it's an infinitely harder problem. Now you might say, Professor Lytle, that's not realistic, but it is. If you ever go to Washington, D.C., like you look at the Air and Space Museum, they'll have the outside made of this highly polished granite. And you take a ladder with a plastic top on it and touch it against that granite. Even if I touch this, this board is almost no friction. So there's zero friction up there, okay? And what we want to find is all the forces, okay? The mass of a ladder is 12 kilograms. Okay? Now, it turns out, I'll mention this because I'm a ladder climber all the time, and a lot of you are going to have ladders someday. There is a proper angle for a ladder. If you look at the rungs on a ladder, they're attached to the ladder angle. And if you look at the top of the rung, you put the ladder so the top of the rung is horizontal. If you have it too steep or too far, then it's not at the proper place. What will happen if you have it too far out? Has that happened? Oh yeah. I've seen guys working on their houses and I'm going, somebody better call an ambulance right now. I already told you about the guy who got dragged off the roof. Okay. Of course, the other thing is, if you put this in too close, then what happens? Then you do a John Belushi in Animal House. You go off, okay? All right? So the question here is find all of the forces involved. No friction at the top, though. So we have a picture. Check. Free body diagram. Well, in this case, the forces are the wall and the ground, and they are acting on the ladder, so the forces come together on the ladder. We consider the ladder, the forces on the ladder. That's what we choose to draw the free body diagram on. Okay? So we draw the ladder, and we have to include here some of these dimensions. This is 4 meters. This is 5 meters, like that. Now, if there is no friction up here at the top, does that mean there's no force? What's the direction of friction? Parallel to the interface. If there was a frictional force, it would be this way. But there is none. It means that the force is horizontal. And it must obviously be to the left. And I want to be consistent with the text. They call this the wall force. Does everybody see why it has to be to the left? The ladder wants to go this way. It's countering that and going that way. And it must be, it can't tilt up or tilt down because that would mean there would be friction. And there's none. So it's a normal force. This is actually a normal force. This is the normal force of the wall on the ladder. It's another way of looking at it. Now down here on the bottom, big mistake. Many people will assume that the ground is directly pushing on the direction right up the ladder. It turns out that is wrong. If you actually look at the diagram in the textbook, they have the ground force angled upward slightly. The ground does not push directly on the ladder. The force is actually not in that direction. But like we did for the hinge force, since we don't know the direction or the magnitude, it's easier to draw it as two components. Obviously, there has to be something to counteract this. What about gravity? Let's look at gravity. Where's gravity acting? Downwards where?
From the center.
From the center. Good. Right here in the middle is mg. And if we want, this is, I think I'll leave it out, but it's 2.5 meters here and 2.5 meters there. Okay? Then there's the ground force. Well, the ground isn't pulling down for sure, it's pushing up. In fact, the ground has to be pushing completely up, straight up. And so, are they calling this a GY? I would call it, well, they call it FC. Okay, I don't know why they do that. But there is a Y component here, and then there is an X component here. I would have called that a G. Force, ground, Y, force, ground, X. Who wrote this book?
It's a cement floor.
Huh?
Cement floor. I think that's where the C came from.
Oh, does it say it's on a cement floor?
Yes.
Okay, okay, all right. Does the fact that it's cement really mean anything?
It means it's gonna hurt more if you fall.
Yes, it is. You ever fallen off a ladder? I have. I like what John Belushi does in Animal House. He just, bam, goes back. Or no, what's the other one? Christmas Vacation. Isn't it Christmas Vacation where Bill Murray, or is it Bill Murray or whatever, I forget, fall? All right. This is actually, it looks complicated, but so what do we apply first? The torques or the first condition? First condition. We apply the first condition of equilibrium. The sum of all the y components on the ladder is 0 because its acceleration is 0. Well, this has no y component. The wall doesn't. And the cement floor, X doesn't. But we have a plus FCY and we have a minus mg. And there you are. The y component, the floor is pushing up with an amount equal to the weight of the ladder. Put in 12 kilograms times 9.8. It comes out to be 118 newtons. So you put in the 12 kilograms. I'm letting you do that calculational part. That's math, that's arithmetic, that's not, All right, let us do the horizontal. The sum of all the x components is also equal to 0. And we have a plus FCX and a minus F wall, which tells us that the force exerted by the wall offsets the horizontal force exerted by the floor. One's pushing it left, one's pushing it right. But we don't know either one. We don't know either one. All right? But at least we know that once we get one, we got the other right away. So how do we get one or the other? Well, if we've used the first condition of equilibrium, now we go to the second. It's kind of a no-brainer. I'm going to take the drawing off here to make room. Anybody want to suggest where I stick the pivot? That sounds disgusting, but anyway. What's a pivot I should use? Which is the only point that has two forces on it? The bottom of the ladder. Obviously, the bottom of the ladder. The bottom of the ladder. So the sum of all the torques about the ladder bottom. Notice how I write it in here. Must equal 0. So does FCY or FCX produce any torque about the bottom? No. That's why we chose it. Okay. So there's a 0 and a 0. I won't write them down. All right. Now, what about gravity and the wall force. Oh man, this is not a 90-degree angle, is it? And this sure the heck isn't a 90-degree angle either. However, could we find those angles? Since we know the opposite and the hypotenuse, could we find this angle and this angle? Yes, we could. And if I know this angle, can I find that angle? Yes, I could. And then and could I find this angle? Yes. And then you use the torque as Fr sine theta. Oh man. Oh man. Well, we could do that, but there's an easier way. Okay. What is the torque produced? Well, first of all, let's look at Fw. Is that, compared to this point, is that a positive? It's this. Is that positive or negative?
Positive.
That is positive. So we have a plus Fw, and how far is that force? What? Well, let me put it this way. This is where you get clever. Let me draw the line of action of this force. I could use this angle and use Fw 5 meters sine of this angle, but I don't want to do that. It's too much work. What is the distance from the line of action of Fw from the pivot? 4 meters. You see that? This distance from here to here is 4 meters. That's it. That is it. You don't have to use Fr sine theta. You can just look at it and say, hell, that's 4 meters. Okay? That's 4 meters, and you're done. Now what about the torque produced by gravity? Is it plus or minus? It's minus. We better have a minus. And it is little mg. Okay, who sees it?
2 meters.
Can we figure out this length?
Oh, wait, yeah.
Yes, it's a 4, 5.
3.
It's a 3, 4. Good for you.
Oh, yeah, sorry.
Yes,
1.5
you get the beer
meters.
tonight. You get the beer tonight. It's a 3, 4, 5 triangle. You could simply use this side is 5 squared minus 4 squared square rooted. If you use hypotenuse squared is opposite squared plus adjacent squared, you can solve this for the adjacent. Adjacent squared is the square root of the hypotenuse squared minus the opposite square, or the opposite squared, and you'll get that this is the adjacent opposite hypotenuse. It's 3 meters. All right, so this is in the middle of the ladder. What is the distance from the line of action of that force to the pivot? 1.5 meters. See, cleverness. You can find all the angles and use Fr sine theta and do all that, but if you're clever, you don't have to. And you solve this, and you get the Fw is, when you find Fw, it's 44 newtons. And immediately, because we this first condition, we get that the x component of the floor force is also 44 newtons. There are multiple ways to do problems. That's why we say, remember, torque is equal to Fd, or torque is equal to Fr sine theta. Either one of these will work and give the correct result. This is a hell of a lot harder because you got to do all the intermediate work of finding the angles, and then you got to plug it in, and oh God, okay? This is much easier, all right? Now, I'm going to stop there for today, but the one homework problem, I believe, that I assigned says this. It says that if the ladder is here, and this is frictionless, we always assume this top is frictionless in these problems. The question is, how far, and you're given the coefficient of static friction between the bottom of the ladder and the floor. I think this is problem, let's take a look at this. I'm just giving you a hint on this so you can get going there. Is this problem? Yes, this is problem 30. Find a formula. You're given this angle here, and you're given mu sub s, and it actually says find a formula for the minimum angle at which it will slip. So you're saying, if I keep bringing this out, how far can I bring it out? What's the angle when it starts to slip? So here is the hint. Here is the hint. You take this problem, but you don't even have to know the length of the ladder is just length L. So you take this problem and you make this L. So the length of the ladder is L. And you don't know the mass of the ladder, so you make it just M. And in this problem, this is Fs max. And what you do, as I said, consider the case where the ladder is ready to slip. If you move it 1 millimeter more, it's going to go. In that case, this horizontal force, for problem number 30, this horizontal force is Fs max. And I think you'll get a tangent kind of thing like you did in one of the other ones, and you can actually say how far can you pull that out. All right? But for those last 3 homework problems again, on Monday after class I will post them. You should do them, know how to do them, but I'm not going to collect them. I am going to collect the ones due on Monday for other section, was it 9-3 and those ones. But these last ones I'm not going to collect, okay? All right, have a great weekend and stay safe. Unfortunately, what is the most dangerous place you can go? Where you want to go on the weekend? A bar. Think about it, okay? If you can stay outside, okay, but inside, you're taking a big chance. How far do you trust another student? Okay.